Hey students, so in this video we're going to go over symbolic arguments. So the goal for this section is to discuss symbolic arguments and determine whether a symbolic argument is valid or invalid. So the term argument has a very specific meaning in symbolic logic. The statements in the following form constitute a symbolic argument. So we have two premises followed by a conclusion. The first premise is, if Rigby goes to work, then Rigby will get paid. The second premise is, Rigby goes to work. The conclusion then follows, therefore, Rigby will get paid. So a symbolic argument consists of a set of premises, two or more, followed by a conclusion. And I have a note here that these are called symbolic arguments because it is generally rewritten in symbolic form in order to determine its validity. So we write the argument in symbolic form. So we'll let P be Rigby goes to work, and we'll let Q be Rigby will get paid. So premise 1, if Rigby goes to work, then Rigby will get paid. The sentence here, the statement, becomes this conditional statement here when we put it into symbolic form. And then premise 2, Rigby goes to work, well, that's just P. So that's our second premise. And then our conclusion, therefore, Rigby will get paid. So therefore ends up getting represented by these three dots, and then Rigby will get paid is just Q. So this part here, this is the argument written symbolically. So that's your symbolic form of the argument. So we'll go over a definition because we want to be able to figure out if these arguments are valid or invalid. So an argument is valid when its conclusion necessarily follows from a given set of premises. An argument is invalid, or referred to as a fallacy, when the conclusion does not necessarily follow from the given set of premises. So test the argument form for validity. So we have our argument in symbolic form. So we're going to test the form to see if it's constructed in a valid way, if it's a valid argument. So to do this, to test it, we're going to rewrite the argument in the following form. You're going to take the whole symbolic argument and rewrite it into a conditional statement. So it's going to be if premise 1 and premise 2, then conclusion. So when we do that, well, premise 1 was the if P then Q, premise 2 is just Q. P. Premise 2 is just P. And then the conclusion was just Q. But this and here is a conjunction, and this if then is a conditional. So this is how we've rewritten our symbolic argument as like a giant conditional statement. Now that we have that, we build a truth table for it. So this was the conditional statement that we constructed out of our symbolic argument, and we construct the truth table for it. And then this column right here that I have darker than the other ones, this is the answer column or main column for the truth table for this symbolic argument. And since it is an implication, and just as a reminder, an implication is a conditional statement that is a tautology, right? So this is a giant conditional statement, and it is a tautology because we have just all truths down that main column, so it's an implication. So this is how we're going to interpret the truth table. If the truth table is true in every case of the answer column, then the statement form is a tautology, and it's also an implication. So we can add that here, implication. And the argument is valid. So if you get tautology, it's a valid argument. If the statement form is not a tautology, so even one of those truth values down the main column, even if one of them was false, then the argument is invalid. Oh, and I realized I had this here. There's my little reminder here. Conditional statements that are tautologies are called implications. Therefore, this argument here that we started out with, this is a valid argument. So when we determine if an argument is valid, we're really checking the form of the argument. You're not really looking at the individual simple statements and their truth values. Couple comments for your valid argument. A symbolic argument is a conditional statement. And recall that a conditional statement is only false when the hypothesis is true and the conclusion is false. If all the premises are true and the conclusion is false, then the argument is invalid. And you also have standard forms of arguments. So these are like known forms. And these are for valid arguments. You have this law of detachment. That's the one we just went over. And this is a known argument form, law of detachment, and it's a valid argument. You also have the law of contrapositive. This is what the law of contrapositive looks like. That's that type of argument right there. If P, then Q, not Q, therefore not P. And that's a known valid argument. And there's a couple more. You have your law of syllogism. If P, then Q. If Q, then R. Therefore, if P, then R. And then another one down here. This is your law of disjunctive syllogism. P or Q, not P. Therefore, Q. And these are also valid arguments. So those are some standard forms. You also have a few standard forms for invalid arguments. There's the fallacy of the converse, which is if P, then Q, Q, therefore P. This is an invalid argument. So that conclusion does not necessarily follow from the set of premises. And you also have the fallacy of the inverse. If P, then Q, not P, therefore not Q. That's an invalid argument. Determining the validity of an argument. So this is your step-by-step, what you're going to do when you're testing out an argument. You're going to first write the argument in symbolic form, identify the premises and the conclusion. You're also going to identify your simple statements like P, Q, R, what those are. Step 2, you're going to compare the argument with forms that are known to be valid or invalid. So once you have your argument in symbolic form, go through the known valid arguments and the known invalid arguments and see if it is one of those. If it is, then you have your answer. You know if it's valid or not. Otherwise, you're going to go to step 3. So if it's not one of the ones listed in the slides above, then you're going to go to step 3. And step 3 says if the argument has n premises, you're going to write a conditional statement of the following form. You're basically going to do premise 1 and premise 2 and ... and so on until you get to the end and premise n. So you're going to take all your premises and you're going to put the conjunctions between them, the conjunctions, the ands. After you have all those premises, then you're going to use your conditional statement and then have your conclusion. So you're going to have to rewrite your symbolic argument into this form. Then you are going to construct a truth table for the statement form that you've come up with. That's step 4. And then step 5, you're going to interpret your table. If the statement form is a tautology, therefore an implication because it's a conditional, then the argument is valid. Otherwise, you're going to say that the argument is invalid. So here we have example 1. We want to determine whether the argument is valid. Compare the argument to a standard form or use a truth table. So the first thing we're going to do is identify our simple statements. So Rigby goes to work at the park. That's P. And then Q, Benson becomes angry. So your first premise here, this first premise is just P or, so disjunction, Q. And then your second premise is Rigby did not go to work at the park, so that's not P. Then you have your horizontal bar that therefore gets replaced with the 3 dots. and then Benson becomes angry, which is Q. So that is the symbolic form for this argument here. And we did see this. This is one of the standard forms. So this is actually a valid argument, and it is the law of disjunctive syllogism. So that's a valid argument. Example 2, determine whether the argument is valid. Compare the argument to a standard form or use a truth table. So we have our first premise says Rigby works hard if and only if Benson pays well. Okay, so P can be Rigby works hard, and Q can be Benson pays well. So that first premise is P if and only if Q, right? Because we have our biconditional right there, right? So we have our double-sided arrow. The second premise says Benson pays well, and, okay, so we're going to have Q and Rigby gets overtime. I don't have that yet, so we'll call that R. And I said Rigby, Mordecai. Mordecai gets overtime. So that will be R. Therefore, and we near a conclusion, Rigby works hard, P, or, disjunction, Mordecai gets overtime. All right, that is the argument in symbolic form. P if and only if Q, Q and R, therefore P or R. This doesn't match any of the standard forms that we saw earlier, so we're going to have to do a truth table for this. Okay, so for this one, this is where you're going to have to make a large, actually let me put it up here, we have it in front of us. We're going to have to make like a large conditional statement out of this. Oh, that's a Q. So we have P, Q, and R, so we're going to have 8 cases. And what we're going to do is we're going to have to put our, right here, we're going to put our premises together with conjunctions. So the first premise, P if and only if Q. Then you're going to do the conjunction and. Then the second premise, Q and R. And then I have like these larger brackets around all of that. And then you're going to use your conditional statement and then your conclusion, which was P or R. But all of that is the conclusion, so you have to make sure you put parentheses around that. Or I would anyway, just to kind of emphasize that. Order of operations would tell you to do the and before the conditional anyway, but I prefer to have the parentheses around it. All right, then we're going to do our cases over here. Usually on the test, yeah, I will have like this part filled in for you, so you don't have to worry about if you're getting all the possible orderings of the true, false for those 8 cases. Okay, let's work on the inside parentheses first. So I'm going to do this set of parentheses here, which is the biconditional between P and Q. So your biconditional is going to be true as long as both sides, P and Q, have the same truth value. In the first case, they're both true. Second case, they're both true. In these cases here, the third and fourth case, P is true, Q is false, which makes the biconditional false for both of those. In the next 2 cases, P is false, Q is true. Biconditional is false. And then in the last 2 cases, both P and Q are false. The truth values are matched up, or the same, so the biconditional is true. Then we're going to do this other set of parentheses with this conjunction. So we're looking at Q, we're looking at R, and we're doing the conjunction, so both need to be true in order for the conjunction to be true, which happens in the first case. And then false, false, false happens again in the, what is this, the fifth case? The fifth case, it's true again. And then the rest are false. Then we're going to do this conjunction looking at the two columns we've just entered. So the conjunction is true here where both of these are true. Then it's false, 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 false for all the other ones, right? The first case is the only case where both this is true and this is true. Okay, then we're going to do this disjunction. So one or the other has to be true. So we're looking at P, the column for P, and the column for R. They're both true in the first case. In the second case, the P is true. In the second case, the P is true. In the third case, P is true. Fourth case, the P is true. And then the fifth case, the R is true. Sixth case, they're both false. Seventh case, the R is true. Eighth case, they're both false. Okay, now we're going to do this conditional. So we're looking at this column here, which represents the truth values for everything inside these larger brackets. And we're looking at this column here, which represents, everything inside this set of parentheses. So the conditional, only false when you have a true hypothesis and a false conclusion. So the first one's true. Second one's true by default, true by default, true by default. The rest of these are all true by default. When you have a false hypothesis, doesn't matter what the conclusion is, the conditional statement is true by default. So this is your main column, your answer column, for this overall symbolic argument that we're testing. And all of those are T's, right? This is a tautology. So this is a valid argument, right? It's a tautology. You can also say it's an implication if you want, because it's a conditional statement that is a tautology. So this is a valid argument, and we test it with the truth table. That's a valid argument. Example 3, determine whether the argument is valid. Compare the argument to a standard form or use a truth table. So if Rigby buys lunch, then Mordecai eats wings. All right, P is going to be Rigby buys lunch. Q is going to be Mordecai eats wings. And so this first premise is a conditional, if P then Q, right? If Rigby buys lunch, then Mordecai eats wings. The second premise says Rigby does not buy lunch, so that's not Q, or not P, excuse me, not P. Therefore, we have a conclusion now, Mordecai does not eat wings, so not Q. So is that a valid argument? Does that conclusion, the fact that Mordecai is not eating wings, does that logically follow from those two premises? Rigby buys lunch. If Rigby buys lunch, then Mordecai eats wings. Rigby did not buy lunch. Therefore, Mordecai does not buy wings. Well, maybe Mordecai still gets, buys his own wings for lunch. But we're not going to guess. We're just going to see, does this match one of the standard forms? Or can we use the truth table to test this? And in this case, this is an invalid argument. This is invalid because it's the fallacy of the inverse. So it's a standard form. So we don't have to do the truth table for this example. Example 4, determine whether the argument is valid. Compare the argument to a standard form or use a truth table. If Benson calls out sick, then Rigby plays video games. All right, P is going to be Benson calls out sick. Q is going to be Rigby plays video games. So this first premise here is if P, then Q. The second premise, Rigby plays video games, or Mordecai watches TV. I don't have that yet, so R can be Mordecai watches TV. So that second premise is Rigby plays video games, Q, or the disjunction, Mordecai watches TV, R. Oh, we have a third premise, which we haven't seen this before. Mordecai watches TV, R, or Benson calls out sick. Disjunction with P. Therefore, and we usually use a horizontal bar to separate the premises from the conclusion. Therefore, Benson calls out sick. P. So this is our symbolic argument. And it doesn't match any of the standard forms, so we are going to have to use a truth table for this one. Okay, so we have if P then Q, Q or R or P, therefore P. So we have P, Q, R. 3 simple statements, so we're going to have 8 cases here. Just jotting them down. And then we're going to put the premises together with conjunctions. So we'll have set of brackets for all the premises together with conjunctions. So first premise, if P, then Q. And second premise, Q or R. And third premise, R or P. Then, right, make a conditional out of this. Then your conclusion, but the conclusion is just P. So I'm going to put that there. So I'm going to work on all these little mini parentheses first, the innermost parentheses. So if P, then Q, that's going to be true, true, false, false, and then the last 4 are all true by default. Then I'm going to do the second parentheses here, Q or R, true, 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 false, in that fourth case there, true, 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 false in that eighth case. Then we're going to do this last little parentheses, that's the R or P. So we're looking at the columns for R or P. It's false here, and it's false here in this last case. Okay, now you have 2 conjunctions. This conjunction, which one do you do? And it really doesn't matter because back when we did a previous section, we went over equivalent statements, and you have an associative law that says if you have P and Q and R, if you put the parentheses here around the P and Q, that's logically equivalent to P and Q and R with the parentheses around the Q and R. So it doesn't really matter. So I'm going to go with like this one here. I'm going to put parentheses around these first 2 to take care of this first conjunction. So this is going to be true, true, false, false, true, 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 false. And I'm going to just box that in lightly. Then we're going to do this other conjunction using the column we just filled in and this column here for this conjunction. So it's true, true, false, false, true, false, true, false. Box this in. This here, represents the truth values for all of the, this whole part here, the whole hypothesis. Then P, I think I'm just going to copy the truth values for P underneath of it, so just so I have it in front of me. And then we're finally doing this conditional with this column here and the P. So we have true, true, true by default, true by default, false, true, false, true. All right, box this in, And this is your answer column for this symbolic argument. And you do have two F's in there. So as soon as you have even one F, it becomes an invalid argument. All right, that's it for this section. Try the homework, and I'll see you in the next one.